Welcome back to the Deep Dive. This is where we take those big, complex topics, pull together the research, and try to give you the essentials, the playbook you need.
Exactly.
And today, this isn't just any deep dive. It's actually a special introductory one. It's part of the DataZen AI podcast, which we've created for the DataZen community.
That's right. And look, for this first one, we have a really clear mission. We know whether you're maybe a seasoned developer or perhaps a product manager or just someone in IT who hasn't really, worked directly with AI yet. All the buzz around generative AI, it can feel like a lot, maybe a bit overwhelming.
Totally agree. So our goal today is pretty straightforward. Let's simplify artificial intelligence, AI, and also generative AI, GenAI. We want to explain what they actually are, why they're suddenly so important right now, especially for your career, your projects.
Right.
And maybe the most crucial part, we want to show you that getting involved with these technologies, adopting them, it's not only incredibly valuable, but it's actually way more accessible than you might think.
Absolutely. It's not some black magic anymore.
No. So we've got a good stack of sources here today. They cover the basics, a bit of the architecture under the hood, and definitely the career side of things.
Right.
Okay. Let's unpack this. All right, so let's start right off top. The whole field, artificial intelligence, AI.
Okay.
When we talk about AI, fundamentally, we're talking about building computer systems, right? Systems designed to do tasks that, well, traditionally needed human intelligence.
Yeah, things like learning, making decisions, solving complex problems, that sort of thing.
And I think the key thing for IT professionals listening today, AI isn't some future tech anymore, is it? It's basically infrastructure now.
That's a great way to put it. Infrastructure. Most people listening, you interact with sophisticated AI systems multiple times a day. Like constantly, even if you never write a single line of machine learning code yourself.
And those real-world examples, they really help take the mystery out of it.
They do.
Like when Netflix instantly suggests a movie you might like. That's not random. It's AI analyzing your viewing habits, comparing them to millions of others.
And optimizing for what keeps you watching.
Or think about Google Maps. It reroutes you because of an accident miles away. It's not just following a simple rule.
No, it's dynamically calculating the fastest route, using real-time traffic data, prediction models. It's learning and adapting constantly.
That's a perfect illustration. That dynamic recalculation shows what AI really is at its core. It's software that's smart enough to learn from data, right? And it gets better on its own without needing step-by-step instructions for every single possibility.
It's fundamentally about learning. That's the key.
Okay, so if AI is about learning, that naturally brings us to the first big subset we need to talk about, machine learning, ML.
Right, ML is really the how. It's the methodology. It gives computers the ability to learn directly from data. So instead of a programmer writing out explicit rules for every scenario.
Which would be impossible for complex tasks.
Exactly. Impossible. Instead, ML uses algorithms to sift through data, find patterns hidden in there, and then use those patterns to make predictions or decisions. And crucially, it improves over time as it sees more data. That's the core of ML.
And our sources point to two main flavors of ML that really form the foundation. First up, supervised learning.
Okay, supervised learning. This is probably the most common type you'd encounter for tasks like classification or prediction in IT. The name supervised comes from the fact that you train the algorithm on labeled data.
Labeled data meaning?
Meaning the data already has the correct answer attached. So building a spam filter. You feed the model thousands, maybe millions of emails already marked as spam or not spam.
Okay, so the model learns the features, the words, maybe the sender, structure that tend to correlate with the spam label.
Precisely. It learns the relationship between the input features and the correct output label.
And the big implication there for IT teams, especially project managers, is the cost, right? Getting that high-quality, accurately labeled training data that can be the most expensive, most time-consuming part of an ML project.
Oh, absolutely. It's often the biggest bottleneck. Which makes the second tech really interesting. Unsupervised learning.
Okay.
Here, the algorithm gets data that is completely unlabeled. There are no right answers provided. You just give the computer a huge data set and basically say, figure out what's going on in here. Find the structure, find the patterns on your own.
So it's looking for like natural groupings or maybe outliers, things that don't fit.
Exactly. Think about, say, customer segmentation for a marketing team. You feed it customer data, and it might identify distinct groups of customers with similar purchasing behaviors without you telling it what groups to look for beforehand.
Okay, that makes sense. What about a more critical application?
Fraud detection is a classic one. You don't train the model on millions of examples labeled fraud. That data is usually scarce anyway. Instead, you train it on millions upon millions of legitimate transactions. The unsupervised model learns what normal activity looks like, typical locations, amounts, frequencies.
Ah, I see. So anything that deviates significantly from that learned pattern.
Gets flagged as a potential anomaly, a potential fraud case for a human to investigate. It finds the weird stuff.
Okay, so AI is the broad field. ML is the learning method inside it. Now, going even deeper, we hit deep learning, DL.
Yep. Deep learning is a specific and currently very powerful subset of machine learning, and its power comes from using artificial neural networks.
Okay, neural networks. Modeled kind of loosely on how the human brain is structured.
Kind of, yeah. Very loosely. But the key is they have layers, often lots of layers, dozens, even hundreds of interconnected nodes or neurons. These multiple layers allowed the system to learn representations of data at different levels of abstraction.
Which lets it capture really complex, subtle, nonlinear patterns that simpler ML models might miss.
Exactly. That layered architecture is what's enabled the big breakthroughs we've seen in things like, highly accurate image recognition, understanding natural language, speech recognition.
And crucially for today's discussion, generating really realistic content.
That's the perfect lead-in. So if you're trying to visualize this, think of those Russian nesting dolls.
Okay.
AI is the biggest outermost doll. Inside it, you've got machine learning. Inside ML, you find deep learning. And then inside deep learning, we find this incredibly creative and powerful subset, generative AI. That's our main focus today.
Okay, generative AI. We said AI predicts, classifies, learns patterns. But GenAI, this is where, like you said, it gets really interesting. It doesn't just predict a label, like spam or not spam.
Yo.
It predicts the next piece of content, like the
Right.
next word or the next pixel, to build something entirely new,
Yeah.
original content.
That's the absolute core difference. Our sources nail this down. GenAI is the type of AI that creates novel outputs, things that didn't exist before.
Like what kind of outputs?
Text, images, music, computer code, even video now. It does this based on the statistical patterns it learned from the massive amount of data it was trained on.
So it builds a kind of statistical model of the input data.
And then uses that model to synthesize, to generate something new that fits that statistical pattern, usually based on a specific instruction or
Right.
prompt you give it.
This difference between classifying things and creating things. We can make that clearer by looking at the two main types of models, right? Discriminative versus generative.
Absolutely. A discriminative model, its job is basically to draw lines, to classify. You ask it, is this thing an X or a Y?
Like the spam filter example, spam or not spam.
Exactly. Or a medical imaging model classifying a scan as showing a particular condition or not. Or a computer vision model deciding if an image contains a cat or a dog. It discriminates between different types of existing data. It recognizes patterns to categorize.
Okay, but the generative model,
Yeah.
it doesn't just draw lines between existing things.
No, it learns the underlying distribution of the data it saw, and then it can generate brand new samples from that distribution. It's a creation engine. You give it a prompt, maybe some starting point, and it generates a whole new piece of data, an image, a paragraph, a song that looks like it could have come from the original training set.
Now, when we talk about the incredible things GenAI can do today, especially with language, well, pretty much everything seems to hinge on one specific breakthrough architecture, doesn't it? The transformer model.
Oh, absolutely. The transformer is, it's been revolutionary, especially for anything involving sequences of data like language.
What made it so different?
Well, before transformers, models like RNNs or LSTMs had to process sequences like words in a sentence one after the other, sequentially. That created bottlenecks and problems with long sentences.
Right, like forgetting the beginning of the sentence by the time it got to the end.
Exactly. The transformer architecture allowed for parallel processing of the sequence elements. It uses this thing called an attention mechanism. That's the secret sauce.
Attention mechanism.
Yeah.
Okay, what does that do?
It allows the model, when it's processing or generating a word, to pay attention to all the other words in the input sequence and weigh how relevant each of those other words is to the current word.
Ah, so it can understand context better, even across long distances in the text.
Precisely. It figures out which words are most important for understanding the meaning or generating the next word no matter where they are in the sentence. This self-attention capability is what gives transformers their amazing ability to handle nuance, complex grammar, and long-range dependencies in language.
So the transformer is generally structured as a sequence-to-sequence thing,
Yeah.
input sequence, output sequence, and it has two main parts.
Correct. You have the encoder stage and the decoder stage.
Okay, what's the encoder's job?
The encoder takes your input sequence, your prompt, basically, and processes it using that attention mechanism. Its goal is to create a rich numerical representation, a vector that captures the contextualized meaning of the entire input, not just the words, but their relationships and significance.
A meaning vector. Okay, and that gets passed to.
The decoder stage. The decoder takes that meaning vector and starts generating the output sequence, usually one piece at a time, like one word or token.
How does it decide which word comes next?
At each step, it looks at the input meaning and everything it has generated so far, and it calculates probabilities. It outputs a probability score for every single possible word in its vocabulary, estimating how likely each word is to be the correct next word in the sequence.
Wow, okay, so it generates this huge list of probabilities. Then the magic is in how it picks the next word from that list.
Yeah.
You mentioned the simplest way.
Yeah, the simplest, fastest way is called greedy search. It just picks the single word with the absolute highest probability score at that specific step.
Seems logical, but maybe not always the best.
Often not. It's very short-sighted. The word that looks best right now might lead you down a path that results in a clunky or nonsensical sentence later on. It optimizes locally, not globally. That's why sometimes AI output can feel abrupt or basic.
Okay, so what's a better approach for getting high-quality, coherent text?
A much better, though more computationally intensive method is beam search.
Beam search.
Instead of just committing to the single best word, beam search keeps track of several, say, possible sequences, the beams that have the highest overall probability scores so far. It explores multiple potential paths simultaneously.
It looks ahead a bit.
Exactly. It evaluates entire chunks or potential sentences, allowing it to discard a path that started strong but ended weakly. It's much better at finding sequences that are globally optimal, leading to more fluent, creative, and logical outputs. If you want quality, you're likely using something like beam search under the hood. Hashtag key model families for GenAI, beyond LLMs.
Now, when people talk GenAI today, especially for text, the term you hear constantly is LLMs, large language models.
Yep. LLMs are definitely central to the current wave. They are a type of deep learning model, and the key characteristic is that they're trained on just truly massive amounts of text data, like huge swaths of the internet, books, articles, code.
Billions of parameters, right? Like Google's PaLM model you mentioned, 540 billion.
Astonishing numbers. And that huge scale allows them to absorb an incredible amount of information about language, facts about the world, reasoning patterns, and so on.
Our sources mention different types of LLMs based on how they were trained or fine-tuned after that initial massive training.
Right. The base models, sometimes called generic language models, are primarily trained just to predict the next word in a sequence. They're great at auto-completing text.
But maybe not great at following instructions.
Not initially. That's where instruction-tuned models come in. They undergo an additional training phase using examples of instructions and good responses. This teaches them to understand and follow commands given in the prompt, like summarize this text or write a poem about.
That makes them much more useful. And then there's a third type.
Dialogue-tuned models. These are further specialized for conversation. They're trained on examples of back-and-forth dialogue, so they get better at maintaining context over multiple turns, adopting a persona, and generating responses that feel natural in a chat setting.
Okay, so LLMs are huge for text. But GenAI isn't just text anymore. We absolutely have to talk about the models driving those amazing AI images and videos. Diffusion models.
Yes, diffusion models are really exciting and represent a different approach. They've become state-of-the-art for image generation pretty quickly.
How do they work? It sounds kind of counterintuitive.
It is a bit. The training involves a forward process where you start with a clear image and deliberately, step by step, add random noise like static until the original image is completely gone, just pure noise. The model learns precisely how to do this degradation.
Oh, so it learns how to turn order into chaos, basically.
Exactly. It learns the reverse of creation. Then, for generation, it does the reverse diffusion process. It starts with a field of pure random noise, and then, using what it learned, it iteratively removes the noise step by tiny step.
Denoising it.
Denoising it, exactly. Over hundreds or thousands of steps, it gradually refines the noise into a coherent image that matches the patterns it learned.
And often guided by a text prompt, right?
Right. That's condition generation. The text prompt steers the denoising process towards the image you described, like an astronaut riding a horse. But they can also do unconditioned generation, just creating novel images based on the training data, like generating realistic faces of people who don't exist.
That iterative refinement process sounds like why the images can be so detailed and photorealistic.
That's a big part of it. It allows for incredible detail and complexity.
It's worth mentioning, though, that these aren't the only generative models ever, right? There were precursors.
Oh, absolutely. Before transformers and diffusion really took off, generative adversarial networks, GANNs, were huge, especially for images. That's where you have two networks, a generator and a discriminator, kind of competing against each other to produce realistic outputs.
And things like variational autoencoders, VAEs.
VAEs, too. They were important for learning compressed representations of data and generating new samples from that learned space. Both GANs and VAEs were foundational and taught the field a lot.
Okay, so all these different powerful architectures, transformers, diffusion models, they lead us to this really important concept for practical use today: foundation models.
Yes, foundation models are key to making all this accessible. Think of them as massive pre-trained models, often LLMs like PaulM or GPT, or large vision models that have been trained on incredibly broad, diverse data sets.
So they have a general understanding of language or images or maybe even code.
Exactly. They're generalists. They have a huge amount of foundational knowledge baked in from that massive pre-training phase.
And the big advantage for you as an IT professional is
You don't have to start from scratch. Training a model of that scale is astronomically expensive and requires immense data and expertise. Instead, you can take a readily available foundation model,
which already understands language, maybe basic reasoning.
and then you adapt it or fine-tune it for your specific task. Maybe you need it to understand your company's internal jargon for summarization or recognize specific products in images for inventory. You can specialize that general foundation model with much less data and compute power.
That makes sense. And tools from cloud providers help here.
Yeah.
You mentioned Vertex AI Model Garden earlier.
Yeah, platforms like Model Garden are crucial. They give teams easy access to these powerful foundation models, Google's own like PaulM, but also popular open source ones like Stable Diffusion for images. They provide APIs, making it much faster to start experimenting, prototyping, and deploying applications built on these models.
Okay, let's shift gears a bit. We've gone fairly deep into the tech.
We have.
But if you're listening, maybe feeling a little intimidated, let's bring it back to why this matters for your career. The number one driver here is simply demand. The demand for people who understand and can work with these AI systems is just huge right now.
It's undeniable. The job market signals are incredibly strong. LinkedIn data, for instance, shows job postings mentioning AI or ML skills have surged something like 74% over the last 4 years. It's explosive growth.
And it's not just for hardcore researchers anymore.
Not at all. It's about embedding AI literacy and skills across many different IT roles.
So obviously the traditional roles are still hot: AI engineer, data scientist, machine learning specialist. Those are definitely booming.
Absolutely. But what's perhaps even more interesting is the growth in roles that kind of bridge the tech and the business side.
Like what?
We're seeing a huge need for AI product managers, people who really get the technology's capabilities and limitations, and also understand the business strategy and can translate AI potential into actual products and features.
That makes sense. So you need someone to connect the dots.
Exactly. And then there's this whole new fascinating role, the AI prompt engineer.
Ah, yes, prompt engineering. We'll dig into that more in a sec. But first, let's just emphasize the incredible versatility that learning about AI offers. It makes you relevant pretty much everywhere.
That's a huge point for career security, isn't it? AI and ML are transforming literally every industry. Think about healthcare drug discovery, personalized treatment plans, finance fraud detection, algorithmic trading, risk management.
Manufacturing, optimizing production lines, predictive maintenance, retail personalized recommendations, demand forecasting.
The list goes on and on. Understanding AI principles gives you a strategic advantage, a seat at the table, regardless of the industry you're in or might move to.
And beyond just the direct applications, learning about AI, even the concepts we've covered, it actually sharpens your core professional skills, doesn't it?
I really believe it does. It forces you to think more systematically about data, about processes, about potential biases. When you start thinking about how to frame a problem so a machine can learn from it, how to evaluate model performance, how to consider edge cases,
That analytical thinking, that structured problem solving.
it transfers. It makes you better at your job, period. Whether you're coding, managing projects, or designing systems. Hashtag the non-coder's advantage, productivity.
Okay, now this next point is really crucial, especially for maybe the non-developers listening, the product owners, project managers, business analysts, folks in IT operations. You absolutely do not need to be building these complex models yourself to get massive value from GenAI.
Couldn't agree more. In fact, for many non-coders, readily available GenAI tools can offer something like a 10x productivity boost right now, today.
10x sounds like a lot, but is it realistic?
I think it is when you consider the tasks it takes off your plate. Think about using ChatGPT or a similar tool, instantly summarizing long reports or meeting transcripts, drafting emails or documentation outlines, brainstorming dozens of ideas in minutes.
Tasks that used to eat up hours of tedious work.
Exactly. Or look at creative work. Maybe you need a quick visual concept for a presentation. Tools like Canva AI can generate decent starting points, saving you from the blank page problem.
Video editing.
Tools like Runway ML are automating basic edits, creating assets, and then you have workflow automation tools like Zapier integrating with LLMs. Imagine automatically summarizing new sales leads and sending the top ones to a specific Slack channel, all triggered automatically.
Okay, and none of those examples require you to write Python code or train anything.
Not at all. What they do require is knowing how to talk to the AI effectively. And that brings us back to the skill you mentioned, prompt engineering.
This seems to be emerging as one of the most valuable digital skills, period.
Our sources really hammer this point home. When you're using these powerful pre-trained foundation models via an API, the whole game shifts. You're not focused on the traditional ML development cycle, collecting data, training, tuning hyperparameters.
You're focused on the input, the prompt.
Precisely. Your skill, your value, lies in crafting prompts that elicit the best possible response from the model. It's about clear communication, understanding how the model thinks statistically, and providing the right context and constraints.
So it's a difference between just asking, summarize this report,
Which might give you a generic, maybe useless summary.
versus asking something like, act as a senior financial analyst. Summarize the key findings of the attached Q3 report for an executive audience, focusing specifically on budget variances exceeding 15% of potential risks for Q4. Limit summary to 5 bullet points.
See the difference? You gave it a persona, a financial analyst, a specific task, summarize key findings, clear constraints, focus on budget variance, 15%, risks for Q4, and a required format, 5 bullets. That specific, well-structured prompt will unlock a much higher quality, more useful output.
Mastering that interaction.
Yeah,
That's the immediate skill upgrade for everyone in IT.
absolutely.
And one final point here, just having AI literacy is becoming non-negotiable.
Yeah, just understanding the basics, what AI can do, what it can't do, its potential pitfalls, how models are generally trained, that's becoming a baseline expectation.
It gives you a real edge in strategic discussions and project planning and evaluating vendor solutions. You need to speak the language.
So for anyone listening who's thinking, okay, I'm interested, how do I actually start playing with this stuff? The good news is, getting started with prototyping GenAI apps is easier than ever. Because, like we said, the focus shifts to prompt design.
Right. You don't need deep ML expertise or mountains of training data just to start building something cool.
Exactly. There are tools now like Maker Suite from Google or GenAI Studio within platforms like Vertex AI that are specifically designed for this. They provide a visual interface.
So no code required initially.
Often no code or very minimal code. You can select different foundation models, tweak settings like creativity levels, and most importantly, iterate rapidly on your prompts. You type in a prompt, see the output, refine the prompt, try again.
Letting you test out ideas really quickly.
Super quickly. You can go from a concept for, say, a customer service chatbot helper or a marketing copy generator to a working prototype you can actually show someone in potentially just hours or even minutes. It really lowers the barrier for innovation.
Okay, but what if you need more? What if you need to customize a model with your own company's specific private data? That's where it gets more complex, right? This is the tuning hierarchy.
Right. If the basic foundation model isn't quite cutting it, or you need it to understand your proprietary knowledge, you need to tune it. And IT folks managing budgets need to understand the options here.
The old school, expensive way is traditional fine-tuning, right?
Yeah, yes. That means taking the entire massive foundation model, billions of parameters, and retraining or adjusting all those weights using your custom data set.
Sounds computationally heavy.
Extremely. It requires huge amounts of computing power, typically GPUs, long training times, and significant expertise. And if you need models for 10 different tasks, you might end up with 10 massive, slightly modified copies of the foundation model. Very costly and inefficient.
Okay, so what's the smarter, newer way?
That's where parameter efficient tuning methods, or PTM, come in, sometimes called PEEF. This is a real game changer for making custom AI affordable.
How does PTM work?
Instead of tuning all billion parameters of the base model, PETM techniques freeze the original foundation model. They don't change its core weights. Instead, they add small, new layers of parameters, sometimes called adapter layers, on top of or alongside the frozen base model.
Ah, so you only train these small additional layers.
Exactly. You only tune the weights of these much, much smaller adapter layers using your specific data. Maybe just millions or even thousands of parameters instead of billions.
And the benefit is?
Huge savings in compute cost and training time. It's drastically faster and cheaper. Plus, you don't create full copies of the giant base model. You have the single base model, and then these small task-specific adapters you can easily swap in and out.
So one foundation model could serve dozens of different custom tasks just by loading different lightweight adapters.
Precisely. PTM is what's making deep customization of powerful foundation models truly feasible for many organizations, not just those with massive budgets. #, busting common myths, the beginner's confidence boost.
All right, before we get into the crucial topic of ethics, let's quickly bust a few common myths, things that might be holding some listeners back from diving in. Myth number 1. AI is only for PhDs and hardcore coders.
Yeah, that's definitely a myth now. Reality check. The rise of no-code, low-code AI tools, plus the power of pre-trained foundation models accessed via APIs, means the barrier to entry is much lower. The most valuable skills are often prompt engineering, understanding the use case, critical thinking, and systems integration, not necessarily advanced calculus or building models from scratch.
Okay, myth number 2. AI is going to take everyone's job, automation anxiety.
Understandable fear, but the reality is more nuanced. Yes, AI will automate and is automating certain repetitive tasks, but it's also creating millions of entirely new roles. We talked about prompt engineers, AI product managers. Think also about AI ethics officers, AI trainers, AI business strategists, people needed to manage, govern, and creatively apply the technology. It's a transformation, not just elimination.
Good point. Myth 3. You need that PhD in computer science to get a decent job in AI.
Again, mostly myth for practical roles. Sure, if you want to do fundamental AI research, an advanced degree is standard. But for the vast majority of AI engineering, data science, and analytics jobs in industry today, employers often value practical, hands-on experience more.
Like, can you actually build things? Use the tools.
Exactly. Demonstrable skills with relevant tools, Python libraries, cloud AI platforms, and a portfolio of projects often count for more than purely academic credentials. Practical ability is key.
Okay, so we've talked about the power, the accessibility, but with great power comes, well,
Responsibility, absolutely.
Right.
As IT professionals start building and deploying these generative tools, the conversation around responsible AI and the inherent challenges is not optional. It's essential.
Companies need guiding principles, right? Like the ones Google outlines.
Yeah.
AI should be socially beneficial, avoid unfair bias, be built and tested for safety, be accountable.
Exactly. Those high-level principles are vital, but they need to be translated into concrete governance practices, review processes, and technical safeguards within your organization. It's not just a mission statement. It has to be operationalized.
And even with principles, the technology itself has inherent challenges we need to grapple with.
Definitely. Top of the list is usually bias and fairness.
Because the models learn from data, and data reflects the real world, warts and all.
Precisely. If the historical data used for training contains societal biases, racial, gender, socioeconomic, the model will learn and likely perpetuate, maybe even amplify those biases. This can lead to discriminatory outcomes in really sensitive areas like hiring, loan applications, even medical diagnosis. Managing bias is a massive technical and ethical challenge.
Then there's the black box problem.
Yeah.
Lack of transparency.
Yeah, especially with these huge, complex, deep learning models, understanding why the model made a specific decision or generated a particular output can be incredibly difficult, sometimes impossible.
Which is a big problem if you need to explain a decision, right? Like in finance or healthcare.
It's a huge problem for compliance, for debugging, for building trust. If you can't explain it, how can you be sure it's fair, safe, or correct? Explainability is a major area of ongoing research.
Third challenge, just the basic data dependence.
Right. Garbage in, garbage out still applies, maybe more than ever. The quality, accuracy, and relevance of the GenAI's output are completely tied to the data it was trained on. If the training data is flawed, incomplete, or outdated.
The model will produce flawed outputs, including those infamous hallucinations.
Exactly. Where the model confidently states something completely false because it's just statistically predicting plausible-sounding text, not accessing real-time knowledge or truth, verifying outputs is critical.
And finally, the potential for outright ethical misuse.
This is a big one. The same tech that generates helpful text or cool art can be used to create deepfakes for scams or disinformation, generate fake news at scale, automate sophisticated phishing attacks.
Raising huge legal, ethical, and societal concerns about identity, trust, and manipulation. Requires constant vigilance, security measures, and likely regulation.
But you know what's really fascinating here? It underscores that the relationship has to be collaborative.
Between humans and AI.
Yeah. GenAI is an incredibly powerful tool for augmenting human abilities. It helps us write better, think faster, create more easily, but we have to be the ones applying critical thinking, judgment, ethical oversight. We need to actively fight against what's called automation bias, the tendency to just blindly trust the output of a computer system, assuming it must be more objective or accurate than a human. We can't do that. The human professional needs to remain firmly in the loop, questioning, verifying, and guiding the AI. #HagOutro.
Okay, let's try to wrap this up with a quick summary of our first deep dive here. Fundamentally, artificial intelligence, AI, is that big umbrella concept, building systems with human-like intelligence.
Yeah. Learning, problem-solving, decision-making.
Then, generative AI, GenAI, is this powerful, creative subset focused specifically on generating new content. Text, images, code, you name it, using sophisticated models like LLMs, built often on architectures like the Transformer or diffusion models for images.
And the key takeaway for IT professionals, whether you code or not, is that the opportunity here is immense. You don't need that PhD to get started. The immediate value often comes from developing prompt literacy learning to talk to these models effectively and leveraging these powerful foundation models using accessible tools.
We talked a lot about how GenAI learns patterns from data, and how new tuning methods like PTM make it feasible to customize these models with your own specific data efficiently. So, before we sign off, here's a final provocative thought for you to mull over.
Okay.
Given that GenAI thrives on data patterns, think about your specific job, your team, your company. What unique data exists within your professional domain? Maybe it's locked away in thousands of internal documents or transcripts of specialized customer support calls, or maybe years of process logs.
Data that no generic model has ever seen.
Exactly. What unique data asset do you have access to that? If you could use it to efficiently tune a foundation model, might unlock the next significant innovation or efficiency gain for your work or your company.
Where's that hidden data advantage? And could GenAI, maybe using PTM, be the key to finally tapping into it?
A great strategic question to think about as you start exploring this space. Thank you so much for joining us on this deep dive and this first introductory session of the Data Zen AI podcast.
Yeah, this was fun.
We'll be back with future deep dives, going into more specifics. We'll definitely unpack LLM architectures more, walk through diffusion models, get hands-on with prompt engineering techniques. So please make sure you subscribe to the Data Zen AI podcast wherever you get your podcasts so you don't miss what's next.
Thanks for listening, everyone.